Alright, this is my Lab 5 presentation looking at the motion of a slinky falling. So, table of contents, we have introduction, data observations and models, code, discussion, and conclusion. So for the introduction, the purpose and fundamental principles behind this, the lab is being conducted to see how a spring falls when stretched and to see if it falls all at once or only after attaining the relaxed length. The fundamental principle at work here is Newton's second law, otherwise known as the momentum principle. A preview of the results, the bottom of the slinky does not start falling until the top of the slinky reaches it. So Newton's second law is the primary physical principle at play here, saying that force equals mass times acceleration. It is known as the momentum principle, and a force is equal to the change in momentum over the change in time. So for procedure, I downloaded a video of a slinky falling and uploaded it to the tracker software. Used the center of mass, calibration sticks, and axes to properly record the data frame by frame. I created a computational model to prove the spring does not move until the top reaches the bottom, and then I compared the computational models and the tracker data in its relation to Newton's second law. So for tracker data, you can see the GIF of the slinky falling right here, and the bottom stays relatively in the same position until the top hits it and then it falls. And the tracker data on the side shows the bottom staying constant at the origin and then suddenly dropping afterwards. As far as initial observations go, it had a start time of 0 seconds, an end time of 0.767 seconds, an initial velocity of 0 meters per second, an initial position of the origin. The system in this case was the slinky, while the surroundings were anything that was affected by it, which is air or gravity. And then moving into my code, I added initial conditions for the objects in the experiment, like the spring with its mass of 0.204 grams. I put in net force equations, including the tension equation and the gravity equation. And then I also created 2 while loops, one to update position before the slinky, before the top of the slinky had reached the bottom, and then another one to update position of the entire thing moving downward. So comparing the computational model to the slinky tracker data, you can see that both of them had a dip around the exact same amount of time, a little bit after 4 seconds, and it all fell to the ground from there. But the initial position maintained 0 all the way up until the top reached the bottom, and then it declined from there. So potential errors, mistakes could have been made using the tracker software. Additionally, the video model, it would have been impossible to not have drag interacting with the falling object. So the computational model could have had some slight errors in it. But moving into the conclusion, the momentum principle, or Newton's second law, is observed in the video model through the object's acceleration, mass, and force interaction. Force grows as mass grows, and the same with acceleration. This experiment proved that a slinky bottom only moves after it's restored to its relaxed length. And the gravity and drag computational model is near exactly like the experimental video of the model movement of the slinky being dropped. Now the slinky maintains its position, or its bottom position, because of the tension force that holds the bottom of the slinky in place until it remains in its relaxed length after the top falls. And once the top falls and meets the bottom and it hits its relaxed length, then the rest of the system will fall to the ground. Thank you.